This sixth type of reaction is whenever you have a carbon-based compound being added to oxygen. This guy is known as an organic combustion reaction. And anytime you have a hydrocarbon, and that's just like it sounds, hydrogen, carbon. If you have a chemical that's made up of just hydrogen and carbon, and you burn it in the air, add oxygen to it, it's always 100% of the time going to form carbon dioxide and water. So if it's just anything with carbon and hydrogen in it, if it's carbon, hydrogen, and oxygen in it, no matter what, if it's either one of these guys and you add some oxygen to these, 100% of the time, carbon dioxide and water are your products. And really, it's just a matter of balancing the chemical reaction at that point forward. These guys, if you see a solid transition metal placed in a solution, these guys, you have a single displacement reaction going on. There's redox reactions, and it says the solid's always going to be oxidized. And then it says, what does that even mean? What's going on there? So if we had solid manganese flakes, be careful, not magnesium, but manganese, a transition metal in the middle of the periodic table. And we were to place that in a solution of copper 2 sulfate. So copper 2 sulfate, it's a solution, so that means you have copper ions plus 2 and sulfate ions minus 2. Well, the manganese solid is going to combine with the sulfate ion. And then your copper ion that is originally with the sulfate gets kicked out to be by himself to be copper, the element. Well, manganese sulfate is soluble just like the copper 2 sulfate. So the sulfate ends up being a spectator ion. It ends up disappearing during the course of the reaction. So what we have left is this manganese on the left, solid manganese. It's the elemental form of manganese pulled right off the periodic table. Manganese, the element, does not have a charge. 0. Manganese, when it's part of an ionic compound, this manganese is really part of manganese sulfate. Ionic compounds have cations and anions. They have a positive part and they have a negative part. Elements do not have charges when they're all by themselves. You can't have a positive without a negative standalone, right? We just canceled out the negative piece of this one. It's there, but we just canceled it out because it's not really doing anything. So manganese on the left, elemental manganese, is neutral. There is no positive part, negative part. It's just manganese, neutral. The manganese on the right, part of manganese sulfate, that's a cation, and in this case happens to have a charge of positive 2. Well, if it used to be neutral, and then over the course of the reaction, it suddenly developed a charge of plus 2, that would mean that it would have to have lost 2 electrons during the course of the reaction. When a substance loses electrons, we call that being oxidized. Well, where do they go? You can't just have a magic wand and wave it and say, make your electrons disappear, right? They have to go somewhere. So if you compare our copper on the left to the copper on the right, copper on the left is part of that copper 2 sulfate. that it would have an anion piece to go with the cation piece. So the copper on the left is the ionic form. It's part of a compound. The copper on the right is elemental copper. If you did this reaction, you would start to see reddish, brownish copper being formed. Solid copper, the kind that you'd find on the periodic table. Elemental copper does not have a charge. It can't. It's just copper. For something to have a charge, you need a negative piece to go with your positive piece, and it's just copper. Neutral. So if the copper on the left used to be positive 2, now it's neutral. The copper must have gained 2 electrons along the way. If something gains electrons, we call that being reduced. You might think that's kind of funny, gaining electrons being called reduced. It's because the charge is being reduced. It used to be a positive 2, and now the charge is down to 0. There's a little gimmick there to help you remember. It's Leo the lion goes grr. And Leo stands for lose electrons oxidation. Grr, gain electrons reduction. So that's what this part over here says. What happens to the solid metal's electrons when it becomes oxidized? What does this mean? Where did they go? It means that during the course of the reaction, when we say the manganese lost 2 electrons, that it was oxidized, again, like no magic wands, they had to go somewhere. So where did they go? They went to the copper. The copper gained those 2 electrons. Your total lost and total gained should always equal one another, because it's the same 2 electrons that they're talking about. It's a transfer of electrons. These electrons are these electrons. It's the same ones, that we're just moving them to a different chemical. So you can't lose 4 and gain 2. That wouldn't make sense, because then some would have to vanish along the way. Okay. You could see here what's going on. We have nickel neutral on the left, nickel positive 2 on the right. So when it went from elemental neutral nickel to nickel plus 2, nickel plus 2, it's part of a compound. This nickel is combining with this nitrate during the course of the reaction. So it's making nickel nitrate. Our nitrate just ends up being a spectator ion, so we don't show him in the reaction. But he's there, right? So if nickel used to be neutral, now is positive 2, it must have lost 2 electrons along the way. It was oxidized. Well, where did they go? They can't just vanish. So if you look at your silver, on the left it's positive 1, and on the right, all by itself, standalone silver. By itself, neutral, not part of a compound, no cation, no anion, just silver. So if it used to be positive 1, now is neutral. When it went from here to here, it gained 1 electron. So if it gained 1 electron, but this one lost 2, how does that work? Oh, because there is a 2 right here. So the first silver gains an electron. The second silver gains an electron. So 2 electrons are gained total, right? Gains 1 electron. Gains 1 electron each. 2 electrons are gained total during the course of that.